Welcome to the Explainer. So, you've looked at calculus before and thought, wow, that's intimidating, right? Well, you're in the exact right place. Today, we're unlocking one of the absolute coolest, most elegant mathematical tools humanity has ever stumbled upon, the calculus of accumulation. We're going to completely demystify a concept called integration. You know that giant, daunting, squiggly line on the chalkboard? It's actually the secret code to how the entire universe accumulates stuff. By the time we're done here today, you aren't just going to understand the math. You're going to see how it literally shapes the physical world around us, from the water flowing in your pipes to the rockets launching into space. So let's jump right in. Okay, let's dive into this with a massive puzzle that gets right to the heart of what we're talking about today. Picture this. You're cruising down a long, open highway. You glance down at your dashboard, and the speedometer gives you this hyper-precise, real-time number of exactly how fast you're going right in that split second. But does that single piece of information tell you how much distance you've actually covered on your road trip? Think about it. Without checking your odometer or, tracking your time, knowing your speed alone doesn't give you the whole picture, does it? You've got this momentary rate, sure, but you are completely missing the total accumulation. So to solve this puzzle, we really need to look at the two distinct halves of calculus. On one hand, you've got differentiation. Think of it like that sports car on the left, which answers questions about immediate rates of change. Derivatives tell us exactly how fast something is changing right now. How fast? But then we have integration on the right, like filling up a jar. That answers the question of how much. Because let's face it, engineers and scientists don't just care about how fast things are changing, they absolutely must know the total amount that has accumulated over space or time.
Now, what's really interesting about this slide is that integration isn't just some abstract textbook equation. It's an incredibly practical mathematical hero. When we're dealing with complex systems that are constantly shifting, moving, and evolving, integration steps in and makes sense of the whole mess. It lets us take all those tiny, microscopic, momentary changes, add them all up seamlessly, and figure out the final total quantity. It essentially grabs all the highly fragmented, split-second pieces of a changing system and stitches them together to give us the complete whole.
Let's ground this in a scenario we can all relate to. Let's bring back our everyday vehicle. Say we have a car and it's traveling at a constant rate of 20 meters per second. That's our rate of change. Every single second that ticks by on the clock, this car moves forward another 20 meters. Now, it's a super simple setup, maybe a little too slow to be passing anyone on the highway, but it perfectly sets the stage for the exact problem integration was built to tackle. We've got this continuous flow of movement happening second by second. So we look at that constant 20 meters per second. That number is our velocity. And velocity is fantastic if you want to answer one very specific question: how fast are we moving right at this exact moment? But we really need to pivot our mindset here. As focused learners, we want to look past the immediate moment and seek the final end result. What if that momentary snapshot of speed just isn't cutting it? What if we have a much bigger, completely different goal in mind for this journey? We want to know how far we've traveled. We want the distance. And honestly, this is exactly where integration works its absolute magic. By integrating that velocity over a specific chunk of time, we bridge the gap between a simple rate and physical reality. We get the actual distance traveled. We're mathematically gathering up all those individual seconds where the car moved 20 meters and accumulating them into one concrete number of total meters. It's this seamless summing up of history. So the crucial point is the perfect mathematical balance happening here. These two operations are exact, necessary counterparts to one another. If you start with your position, your total distance, and you want to find out your velocity, you take the derivative. You go from the accumulated amount back down to the momentary rate of change. But if you're starting with your velocity and you need to get back to your position, you use the integral. You go from velocity to position. They form this beautiful, continuous loop of mathematical logic, literally two sides of the exact same coin. Let's escalate our journey a bit here, because integration goes way beyond simple road trips. We've talked about a car, but what about massive critical infrastructure? Picture a huge municipal water tank. Water is flowing in at a certain measurable rate. Just like the car's speedometer, that flow rate tells us exactly how much water enters the tank every single second. But say you're a city planner or a civil engineer trying to keep a whole city hydrated. Knowing what happens in one isolated second, that's not your main concern at all. Your concern is the big picture. And integration scales up those tiny second-by-second drips and splashes into a massive practical measurement. It lets an engineer mathematically calculate exactly how much water is sitting in that tank after an entire hour, or even a whole day has passed. It accumulates thousands of individual seconds of water flow into a total volume. I mean, this is exactly why integration is absolutely vital to modern society. It allows us to plan, predict, and manage the essential resources of our world over vast periods of time.
Now take a look at the seemingly tiny number, 0.2 kilograms per second. Looks like nothing, right? But context is everything. In aerospace engineering, this represents a spacecraft engine's fuel consumption during a super delicate orbital adjustment. To put that into perspective, the mighty Saturn V rocket burned through roughly 13,000 kilograms of fuel every single second during launch. That's insane. Here we're just looking at 0.2. But the stakes? Just as high. Every second, 0.2 kilograms of fuel are burned, and out in the vacuum of space, AAA isn't coming to bail you out with a gas can. The margin for error is absolutely zero.
And this brilliantly illustrates the universal power of integration. See, the fuel flow rate only tells the astronauts how quickly the fuel is currently being consumed. But to actually survive and execute a critical orbital maneuver, the flight computers have to use integration. Integration calculates the total fuel used during that entire burn. It makes sure that the accumulation of those 0.2 kilogram bursts doesn't leave the tank empty before the maneuver is completely done. Integration is, quite literally, keeping the spacecraft functioning and the astronauts alive.
Let's move to and see how this builds into something you can actually visualize. This is usually the huge aha moment for so many learners. We've been talking about integration as accumulating changes over time, but it has this stunning geometric interpretation. If you plot your rate of change on a graph, like say speed on the vertical axis and time on the horizontal, the physical space bounded underneath that line represents your total accumulated quantity. You are literally multiplying the horizontal time by the vertical rate to get your accumulated total. It's just beautifully visual. And the versatility of this geometric truth is just massive. Just think about some of these real-world applications. If you've got a graph showing velocity over time, the area under that curve gives you your total accumulated distance. Graph power over time, the area underneath gives you total accumulated energy, which, fun fact, is exactly how your home's monthly electric bill is calculated. Graph electrical current over time, and boom, the area gives you the total electric charge that passed through a circuit. One simple geometric concept powering our entire understanding of motion, energy, and electronics. Look, if there is one sentence you take away from our entire explainer today, let it be this exact phrase. It perfectly anchors the relationship in your memory for good. Differentiation tells us how fast things change. Integration tells us how much we have in total. It's the ultimate balance between the fleeting reality of the present moment and the accumulated weight of history. Really, it's just the perfect, elegant summary of the calculus of accumulation. So we've seen how integration calculates the distance of our cars, the vital water in our cities, the precious fuel in our spacecraft, and the energy lighting up our homes. It fundamentally calculates the accumulation of our physical universe. But I want to leave you with a bit of a provocative thought today. Think about your own habits, your daily learning, your small momentary actions. If integration works for the physical world, what small rates of change are you accumulating in your own life? Thank you so much for exploring this with me today. Keep asking great questions, and I'll catch you in the next explainer.